So I'm going to talk more about specifics of this upcoming eclipse since everybody's going to be trying to observe it. This is a picture that I took actually in 2017 from Grand Banks, Nebraska. I think was the name of the town. Yeah. So here you can see it was just at the instant the sun disappeared, and you can see there's a little. This is called the diamond ring effect. So you can actually see that the sun is just barely peeking through some of the valleys there just before it disappeared, and you can see the atmosphere of the sun on the outside. This is called the corona. If you're in the path of totality, it's safe to look at the sun. Look at the sun when this phase is happening, and you'll actually be able to see the outer atmosphere of the sun. So it's a very cool thing to look for. But one of the things that most people want to know is, where is the eclipse going to be visible? And of course, one of the easiest way to do that is visually. And here you can see a map. So you can see that for this upcoming eclipse in 2024, the path of totality kind of runs diagonally. It comes up through Mexico, crosses into the United States, up through the Midwest, and then up through eventually it ends up going up through Maine and Nova Scotia and even Newfoundland out there. So this is the general path that you're going to see. This particular map also shows you percent coverage. You're going to get 100% of the moon, of the sun covered by the moon if you're in the path of totality. But of course, these lines that run parallel to that, you can see the 0.8 here represents people along that line get 80% coverage, 60%, 40%, 20%, and so on. And those are all, this is the property of SolarEclipse. You can just ask for the eclipse map for a given eclipse, and it will generate a map for you with all those features in it, as well as some contact points that are a little technical, the P2s and the P1s and such. So if we zoom into some of that and we want to look more locally, some additional maps here. Here we can see the area where it comes on land in Mexico, and you can see that the shadow first starts to come on land near Mazatlan in Mexico, and kind of continues on. Maximum eclipse where the axis of the shadow is directly pointed very close to the center of the Earth is going to be near Torreon, Mexico. And it's going to keep going, and then it'll eventually cross the Texas border here into the United States up here. Now, if we proceed on and we keep following the path of totality, once it crosses into Texas, you can see that it continues up through a little bit of Oklahoma, not a lot of it, continues up through Arkansas, and eventually up into Missouri up here. And then I'm going to keep scrolling down, give you kind of a stages of the eclipse here. And notice that as we progress, the shape of the umbra, which is these darker circles here, they start to become more elongated. The reason for that is that by the time the shadow of the umbra of the eclipse starts to hit this part of the Earth, the shadow is making a glancing angle with the Earth. And so you're actually starting to get a little bit more of an ellipsoidal shape to the shadow. And so by the time you get up into Illinois and Indiana and things like that, it's really starting to look elliptical. Eventually crosses up here into Lake Erie, continues on into Maine, and into far eastern Canada, southeastern. And then toward the very end, it's going to go into Newfoundland, and you can see how elongated the ellipse is here that represents the umbra. It's very distorted because at this point the shadow is making a very glancing angle with the Earth. So that's kind of the progression of the path that the shadow is going to make across the Earth. That you can see, here's the textured Earth here. You can see here's the shadow as observed from the sun. You can see as it progresses, the shadow starts to make contact. Umbra hasn't touched yet. There's the umbra. So it's starting to touch the Earth there. As we progress, here we're approaching Mexico. There's the umbra. That tiny little black dot in the very center is the umbra. Everything out here is the penumbra. So everything in this gray area out here will see a partial eclipse. Only people within that little black dot right there are going to see totality. So as we keep progressing, the Earth rotates as the shadow moves across. And it continues on. So here's an example of what you would actually see from the ground, not from space like we've seen up till now. From the ground, what will the sky look like? So I've got a manipulate here where I've got hours before the eclipse for 3 different locations: Minneapolis, Champaign, and Carbondale. So if we're in Minneapolis, let's start here. So here you can see from Minneapolis, we're not going to see a total eclipse. You're going to see a partial eclipse. So the sun, you'll see the moon block part of the sun, but not all of us. If we click to Champaign, which is where I'm observing from, well, that's where I'm at right now. It's not where I will be. But here you can see It gets very close to totality, but we're still partial. There's a little bit of the sun still visible. Here in Champaign, we're going to have something like 98% coverage. This is still not safe to look at with the naked eye. You have to be very careful when you're actually observing eclipses that the moon is completely covering the sun before you can look at it with the naked eye. This still requires eclipse glasses or some kind of a solar filter if you're looking with a telescope. So make sure you're very careful with that. If we go down to Carbondale, which is in southern Illinois, they're in the path of totality. And from there, you can see the moon does cover the sun entirely. So from here, we will see a total eclipse. So that shows that location is important. Um, it drastically affects what you're going to see. Now, um, sometimes it's a little bit interesting to do a more of a quantitative approach rather than visual. How does this eclipse compare numerically to other things? So first of all, one of the things you can do with the new solar eclipse function is you can query for properties. By default, if you just feed in the date of an eclipse, you get the date of the maximum. So here you can see it's at 1300 hours on April 8th, 2024, 17 minutes after the hour. That's when the maximum eclipse is, when the shadow axis is almost directly pointed at the center of the Earth. Where is that going to be? Right here near Torreon, Mexico. So here you can see I've asked for the maximum eclipse position. That's down here in Mexico. So that's where you'll get the most circular shape to the umbra for this particular eclipse. From that location, you'll see that the maximum eclipse magnitude is actually bigger than 1, which means the moon is larger than the sun by a little bit. So it's about 5% above there. So the bigger that number is, the longer the eclipse will last. So you want that number to be as much above 1 as possible. From a given location, though, this is for the maximum location. That's that place near Torreon, Mexico. That's what it's there. From a given location, though, here we do geoposition of Champaign. You can see the local maximum eclipse magnitude is less than 1. So here you can see we're right about 98% from here in Champaign. But in Carbondale, it's over 1. So here you can see kind of a numerical result rather than a pictorial result of how things will shape out. Here you can see that from Carbondale anyway, you can see where it does actually get up here, and then up here you get during totality. But you can see how the magnitude changes here with time. You can also calculate the times of the eclipse. So here we're talking about totality when you talk about local umbra contact date 1. Once again, we're observing from Carbondale. This is a place that's in the path of totality, southern Illinois. We can see that it happens at about 1:59 p.m. So almost 2 p.m. is when totality will start. And then it will end at 14. So just a few minutes later, it only lasts, and you can, there's only about 4 minutes, right around 4 minutes from Carbondale for the totality. Beyond these individual queries that you can do for the solar eclipse function itself, we also have a Wolfram function repository item that is called the Total Solar Eclipse 2024 Explorer. And you can use natural language. So if you do Control equals in Mathematica, or if you use Wolfram Alpha Notebook Edition, you can just type this into your input fields. Explore the solar eclipse of April 8th, 2024. And when you resolve that, you can see that it becomes this WFR with no arguments, and it generates a manipulate. And this manipulate allows you to put in a location that you want, Champaign by default. You can specify what map you want to view, whether it's centered on your location, whether it's centered on the umbra, like where the umbra is at an instant in time, or whether it's the global map. And you can actually change the slider here. I'm going to decrease the magnification just temporarily so that I actually try to play with this. I'll enhance it again here in a second for the text, but it makes it easier for me to see the entire output. This is quite a bit of information presented in this output pane here. But here you can see if I move the slider, but this allows you to change the time. And if you choose the time, so at the time that I've got the slider here, you can see that it's still off the coast. I'm going to move forward here. So here we've chosen a time that's about 2 p.m. Central Time, and you can see that it's moved into Indiana by that time. So here you can see the appearance from Champaign at that time. Champaign is actually right about here on the map. So that's Champaign. That's where I've set the location to view from. You can see the shadow is actually over here in Indiana at that time. You get all the properties, both the global properties, of the eclipse at that time, as well as the location dependent properties. You can see the width of the shadow path and the speed at that time instant. So I encourage everybody to play around with this, but there's a lot of information here, so make sure you've got a nice good sized screen so that you can see everything. And now I am gonna compare this. I mentioned comparing earlier. That was more of a numerical approach, but now we want to compare this to the 2024 eclipse to the 2017 eclipse. How do they compare to each other? They were both total. I've got a little bit of code here where I initialize, to get the dates, and then I've got a little utility function that I'm going to use called property compare. This is all in the notebook that you guys can download, so you can see, you can analyze the code if you want. Um, but the idea is that we want to compare the two eclipses to each other. So this one here is just a visual comparison. We'll get back to a numerical comparison here in a second. But you can see the 2017 path was diagonal, but it started over here in Oregon, kind of came diagonally, cut down through southern Illinois, down here in Carbondale, and then continued off into the Atlantic through the southeast coast of the United States. The eclipse in 2024 is also diagonal, but it kind of comes from the almost perpendicular to the previous path. You can see that it comes in from Mexico and comes up this way, once again passing through Carbondale. So Carbondale is kind of a bullseye for both eclipses. So people down there, it's normally a pretty obscure town, but they're pretty proud of the fact that they were at the bullseye for both eclipses. So, but it's going to go up through Indiana, Ohio, once again up through the Great Lakes, the eastern Great Lakes anyway, and then up through northern New England and Maine and eastern Canada. Numerical comparison. Here you can see, I've got a comparison here where you can see the solar eclipse values for the 2017 eclipse for the umbra path and for the 2024. And you can see with property compare the function here, it gives you just the nice result here that the umbra path width in 2024 is wider. So it does last longer. And that's partially why there, because the path width is wider. The umbra is larger on the Earth than it was in 2017, and therefore the eclipse will last longer than it did. It was about 2.5 minutes, if I remember right, for most locations in 2017, and in 2024, it's going to be 4 minutes, or a little, just slightly over. It's not the longest you can have. You can actually have them up to about 7 minutes, but unfortunately not this year. We could also compare the maximum eclipse magnitudes between the two eclipses. So we can see that, once again, they were both bigger than 1. This is the maximum eclipse magnitude. It was a little bit over 1 here, and it's even more above 1 in 2024. Once again, the magnitude is bigger because the umbra is bigger, and so you get a longer lasting eclipse the more above 1 this is. The apparent radius, you can do that numerical if you want. It's more useful to do this visually, which I've done below here. But here you can see the sun's apparent radius in 2017 and 2024. They did differ a little bit just because the distance of the Earth away from the sun. And the same thing with the moon's apparent radius. They differed between 2017 and 2024. So here you can see the moon's radius is almost 0.28 degrees. It was only 0.26 degrees in 2017, or the sun was. So it was the sun was 0.26 in 2017 and 0.26 in 2024. So the difference wasn't that big. They're more distinct in 2024 here. So anyway, here's a visual representation of the moon and the sun. You can see that the moon is the gray disk, is larger than the yellow circle. That's the sun. So total eclipse. That's 2017. See how close they are. And in 2024, that difference is bigger. You can visually see that. So this is why we get a little bit of a longer eclipse in 2024. We can also compare the shadow speeds. Now, I will have a caveat to that here in a second. You can see the speed of the shadow. This is in Carbondale. So this is at a particular location on Earth. You can see that in 2017, the speed was 650 meters per second. It's 838 meters per second. But keep in mind, Carbondale is not at the location of the center of the eclipse in 2024. So this speed depends on where you're measuring it at relative to the maximum eclipse. So visually on a graph here, it looks like it was moving way faster. The reason why, there's a little bit of a bias here. This curve you see here is for the 2017 eclipse. You can see how the speed changed as time went on. So here was maximum eclipse, And here you can see we're actually measuring at the time of totality in Carbondale is very close to maximum eclipse. The speed we're measuring there is about 650. That's the number you see right here. But if you look at the eclipse in 2024, Carbondale's out here, maximum eclipse is way back here. So you can see that we're measuring on the uptick. By the time the shadow hits Carbondale, because the shadow is moving at a glancing angle across the Earth, it appears to be moving much faster. And so it's really hard to compare these velocities because you're not really measuring at the same relative position relative to the maximum eclipse. So you have to be careful when looking at shadow speed. They're neat to look at, but they're hard to compare. We can also do some ratios of the sun moon distance to see how that's changed from 2017 to 2024. So here we've done the ratio of the radius of the sun and the moon. It's about 400 times. And here we want this we want to know how many days have passed from the beginning of the year until the eclipse. This will be useful for the calculations that I'm going to do here. So in 2017, there were 232.559 days that passed from the beginning of the year until that instant in 2017. So here you can see a plot that shows you basically the ratio of the distance between the sun and the earth and the moon and the earth plotted. Now, this is a little bit cryptic here, but I'll explain what we're saying here. So points that are at the top are perigees. These are points where the moon is closest to the earth in its orbit. The line corresponds to a point where anything above this is a possible total eclipse if the moon happens to move across the face of the sun. So in order to see a total eclipse, it needs to be above this line, and preferably you want it to be near one of these peaks because that's perigee. That's when the moon is going to be closest to the earth. And so you can see in 2017 we were near a perigee, but not at the very tip. We were kind of off to the side a little bit, and it's not even, some of these others were the moon was much larger relative to the sun than it is in 2017, but this is where we were. So here I'm going to do the same thing for the 2024 eclipse, and here you can see we're very close to perigee. So we're very close for the current orbit of the moon. But if you compare where the Earth is in its orbit to the sun, you can actually get peaks that are even higher than this location. So if the eclipse had happened out here, we would get an even longer eclipse. So this one, because it happens near perigee, it is total. It's above this line. We're closer to perigee, so you get a total eclipse that's larger. But it could be even bigger had the eclipse happened at, say, one of these peaks. You might start pushing 6 or 7 minutes or something like that if you're out here. Here, we're going to get about 4 minutes. So a little bit of a cryptic thing. The code for all these is behind these closed cells, so feel free to look at this when you download the notebook and look. But it's kind of an interesting way of visually representing the eclipse differences. Yeah, here's an example of an eclipse that well, you can see that it's possible for the moon to be like way down here if you pick it at a different date, and that would not be a total eclipse. So this is after so that's the next eclipse after the total one. So yes, that's what that's this is one where I did this for the next eclipse that follows that. There's one toward the end of the year, closer to the end of the year, and you can see that eclipse that's annular because we're below the line here. And then here, once again, I mentioned this verbally, but here you can see if you compare the local umbra duration, once again in Carbondale, you can see that in 2017 it was only 2.7 minutes long, but in 2024 it's 4.2 minutes long. So this eclipse should be a little bit nicer. I want to deviate a little bit here away from the eclipse itself and talk about a couple of other things that are a little bit slightly unrelated to the eclipse, but still relevant because they might have an effect on things that you can see. Solar activity can be quite interesting. It affects how big the corona on the sun is, the outer atmosphere. If it's very active, the corona will be very large and kind of puffed out and expanded. And there's also sunspots. So if you have eclipse glasses or a filter on your telescope, and you can look at the sun prior to the moon covering it, you might be able to see sunspots. And so if we compare how things were in 2017 compared to 2024, you can see I'm plotting using this resource function here, space weather data, to get the sunspot counts. And you can see that in 2017, we were near a solar minimum. So there weren't a whole lot of sunspots at that time. We were kind of approaching a solar minimum. But here in 2024, we're actually approaching a solar maximum. And so in theory, solar activity should be better in 2024 than it was in 2017. So there can be more things to see. This changes on a day-to-day basis. We also have another thing to show. I just evaluated it this morning. So you can see right now, though, even though we're near solar maximum, unfortunately, the sun is a little bit blank right now. This is an image taken this morning. Essentially, you can see there's one sunspot that's starting to rotate into view. So between now and Monday, this will rotate a little bit more onto the face, but it doesn't look like we're going to get a really active face of the sun to look at, unfortunately. But it's something that you can pay attention to. There's another instrument you can use with this solar image Wolfram function repository item. This is the SOHO satellite and its view. It can create artificial eclipses by putting a mask over the sun, and you can see what the corona looks like right now. And you can see right now there's a couple little outbursts and things like that, some streamers that are coming out. But in general, this is kind of an approximation of what you might see on eclipse day during the eclipse. It won't be blue, of course. The sky will be kind of darker than that, hopefully, assuming clouds aren't blocking your view. That's another concern that I'll get to here in a minute. But these are things that you can pay attention to during totality, though. You might be able to see the corona, and you might be able to see some of these streamers and things outside the disk of the moon and the sun. So you might be interested to look for some solar sunspots and looking at the shape of the corona. Some additional things. When the moon covers the sun, the sky will get dark. It won't be pitch black, but it will be much darker than it is during the day, and you will be able to see brighter objects, not just the sun and the moon. So these are things you can look for during the eclipse. And so here I've got a few initialization things where I'm setting the position for Carbondale, Illinois. You can see that I'm setting the date for the time of maximum eclipse in Carbondale. I'm computing the position of the sun for that date and position. I've got a utility function that allows me to accurately compute the position of a comet called Comet 12P Pons-Brooks, which is currently in the sky. It's not super bright. It's technically naked eye. I think you probably need binoculars if you want to see it, but this will allow us to compute its position. Here you can see where the comet's at in the solar system. Here you can see a solar system map showing you where Pons-Brooks. Ignore the size scale. The scale is off here from the sides. The comet is not going to be a physical sphere this large. This is just a placeholder, but you can see as I rotate, you can see the comet is kind of diving down through the solar system. So here you can see the moon down here and the sun. They're eclipsed at this point in the astrographics. 24 degrees away, we've got the comet up here and Jupiter over here. Jupiter should be fairly easy to see. So if you're out there looking at the eclipse, the sky is dark enough, you'll definitely see Jupiter. The comet will be here, but it will not be this bright. You're probably going to need binoculars. I think it's technically probably about fourth or fifth magnitude for those of you that know the astronomy magnitude scale. So technically naked eye, but my guess is that you're not going to have much sky contrast. The sky is going to be still relatively illuminated, kind of a dark blue as opposed to a black. So you're probably going to need to have binoculars if you want to see the comet. But if you find Jupiter and then go up and to the right of Jupiter, you might be able to see this comet. So something else to try for. Here's an all sky view. Here's the horizon. This is looking at the whole sky. Looking south, the moon and the sun will be pretty high in the sky. We're going to have Venus over here and Mars. So two bright planets are going to be over here to the right of the sun and the moon. And then to the left, you're going to see the comet and Jupiter up here. You'll have Orion over here as some of the brighter stars. The brightest star in the sky, Sirius, other than the sun anyway, is going to be low in the southeast. So these are some other things that you can look for during totality. If the sky is clear and you're in the path of totality, you can try to look for some of these brighter things. The sky will not be black. Just keep that in mind. So only the brightest objects in the sky are going to be easily seen. Otherwise, you may need binoculars. But if you do use binoculars, be very careful. Once the sun comes back out, do not ever point binoculars at the sun unless you have special equipment allowing that to be done safely. Something else that we have to be aware of is that April is about one of the worst months possible to have an eclipse. And it's spring in the Northern Hemisphere. And so here you can see, if you look at the last 20 years and the trends based on that, this is kind of a mean cloud cover. So red here is good. That means more sun. The darker blue you get, the more obscuration, the more coverage of clouds you get. And so you see through most of the path of totality, we're in this blue areas. So there's very few places, even historically. In fact, in Maine, historically, it would be totally cloud covered, but parts of Texas wouldn't be too bad. But you get some blues and stuff in the Midwest here too. So overall, not great historically. But if you look at the forecast, they're just starting to issue forecasts, and we're getting close enough now that you can start to rely on the forecast more and more. What do we think it's going to do this year? Not just based on historical trends, but this year. So I downloaded this picture from the NOAA this morning, and this is their current forecast for Monday. You can see in their legend, you want blue. Blue is clear, the gray is cloudy. So here you can see if you're in Carbondale, it shouldn't be too bad. It's going to be relatively clear. If you're down here in the path of totality of in Texas, you may be in for a bad time. They're currently calling for clouds down here in Texas. So for those of you that are planning to travel down to Texas, hopefully you've got other things you can do when you're there, because you might miss totality if the cloud cover is very thick down there. Also up here in Maine, it's expected to be totally sunny, which is the opposite of what you see in this, where here in this map, the color code's kind of reversed, but here it's like totally obscured historically. This year it's going to be sunny. So this is a great place to be this year based on the current forecast if it holds. I'm going to be in East Central Indiana, so I'm kind of in this 50% mark here. So I'm kind of hoping for the best, but that's where my family is. So I'm going there either way. So hopefully you guys can start paying attention to the forecast, and hopefully wherever you guys have planned to observe from, the weather will treat you well. Hopefully you're not going to this area of Texas because it's not looking promising. Hopefully you're not going to northern Ohio. Um, so some other resources, though, that I do want to point you at. We have precisioneclipse.com. This allows you to enter your location and find out the timing and the coverage of the eclipse from your location that you specified.